You see these massive trains, right? Millions of tons of steel just gliding along these tiny tracks. But have you ever stopped to think what actually keeps them on there? It's not just the tracks themselves. There's this hidden science, this incredibly delicate balance of forces where even a tiny mistake can have absolutely catastrophic consequences. So let's dig into the science that keeps trains on the rails and what happens when it fails. To really get this, we've got to go back. Let's set the scene. Santiago de Compostela, Spain. It's a summer evening in 2013. A high-speed train is approaching a really tight curve just outside the city. And what happened next? Well, it would become a tragic but incredibly important lesson in railway physics.
So what went wrong? It was this perfect storm of factors. You had this super heavy locomotive, right? And it was pulling a bunch of way lighter passenger carriages. When that train slammed into the curve at nearly double the speed limit, all that immense sideways force had to go somewhere, and it hit the lightest part first, lifting one of the carriages right off the tracks and starting this devastating chain reaction.
And look, this wasn't just about human error. This was a fundamental failure of physics. So let's get right to the core of it. What's actually happening when a train literally fails to turn? Right. So what is it? What's this invisible force can make something so huge, so heavy, so seemingly stable, just jump right off its path? Well, the answer is a phenomenon that engineers have been wrestling with for over a century. Okay, so to really get why trains derail, we first have to flip it. We need to understand why they stay on the tracks in the first place. And it all boils down to this constant, invisible battle of forces happening right at that tiny point where the steel wheel meets the steel rail. Yep, there's a technical name for this moment of failure. It's called flange climbing derailment. The flange is that little lip on the inside of a train wheel. Its whole job is just to keep the train guided. But when that sideways pressure gets too intense, that little lip is literally forced to climb right up and hop over the rail. All right, let's break down this battle. It's actually pretty simple. On one side, you've got the stabling force. Engineers just call it Q. Think of this as the good guy. It's simply the massive downward weight of the train, pinning the wheel to the track. But then on the other side, you've got the villain, the flange force, or Y. This is that sideways force. It's especially nasty on curves, and it's always trying to push the wheel outwards. So Q keeps it safe, Y pushes it towards danger. And it honestly all boils down to this one simple thing. Derailment happens the moment that sideways Y force overwhelms the downward Q force. The second that push outwards is stronger than the weight holding it down, that's it. The wheel climbs and the train leaves the track. The absolute key to safety is making sure Q always wins that fight. Okay, so you'd think making sure that downward force is spread out evenly would be pretty straightforward, right? But for decades, oh man, it was anything but. It was this super frustrating, imprecise process that was, frankly, more of a dark art than a science. Check out this quote. It just nails the problem. Setting the suspension to balance the wheel loads was seen as a black art. Experienced engineers had their own tricks, but the knowledge was passed down by word of mouth. Kind of like that game of telephone, getting all distorted along the way. I've got the perfect analogy for you. Think about a wobbly table at a cafe. You know the drill. You jam a napkin under one leg to stop it from wobbling, and what happens? Now a different leg starts to wobble. That is exactly the problem with balancing a train. You adjust one corner, and you throw all the others out of whack. It's a super complex, interconnected puzzle. And this led to this absolutely mind-numbing, tedious process. Engineers would weigh the wheels, then basically take a guess at what adjustments were needed using these little metal plates called shims, and then they'd have to do it all over again, and adjust again, and measure again, and again, and again. You get the picture. Pure trial and error. It could take days to get just one single vehicle right. But what if you could take all of that guesswork out of the equation? This is where the story gets really, really cool. That old, inefficient black art was finally replaced by precision engineering, turning it into a data-driven science. And the breakthrough came in the form of a predictive digital tool. It basically takes all those messy variables, the stiffness of the springs, the vehicle's geometry, the weight, and it just crunches the numbers and tells you exactly what to do. I mean, just look at the difference here. The new method is so elegant. You measure the vehicle's current state, the software calculates the exact fix required, and you implement it just once.
No more guessing. No more, let's try this and see.
So, how does this thing actually work? Well, the system gets super accurate measurements of the load on every single wheel. Then, and this is the magic part, it uses this really sophisticated mathematical model to calculate the exact thickness of the shims needed to perfectly balance the vehicle. It not only solves the problem, but it creates a digital record, turning that old mysterious art into a repeatable, auditable science.
Okay, that all sounds great in theory, but does it actually work in the real world? Oh yeah, the numbers from a major case study speak for themselves. So let's look at the Hitachi rail fleet. We're talking about some of the UK's most modern high-speed trains, and, well, they were facing a pretty serious challenge with this exact wheel balance issue.
This was the number that set off all the alarm bells. Investigators found that some vehicles had a wheel load imbalance of 12%. Now, to put that in perspective for you, the absolute maximum accepted safety limit is only 5%. These trains were running at more than double the safe tolerance, creating a very real risk of derailment. And here's the after picture. Once they implemented this new tool, look what happened. The imbalance was brought down to less than 4.5%. That's not just squeaking by. That is comfortably and consistently under the critical safety margin. It was a massive improvement, all achieved with precise calculation, not guesswork. The safety gains are obviously the most important part, but the efficiency gains are just staggering. Get this, what used to take 7 days of frustrating trial and error adjustments could now be completed in just 4 hours. That is a 12-fold reduction in maintenance time. And that had a huge knock-on effect for the whole maintenance operation. By getting it right the first time, every time, the need for vehicles to come back into the depot for rebalancing was cut by 80%. This means more trains are available for service, and maintenance resources can be used way more effectively. You know, when you step back, the story here is actually incredible. We're talking about a complex life-or-death engineering problem. And it wasn't solved with a bigger wrench or a stronger piece of steel. It was solved by translating decades of human expertise into a simple predictive model, basically into a spreadsheet. It really makes you wonder, doesn't it? In our world of complex systems, how many other life-saving innovations are just sitting there, waiting to be found, hidden inside a spreadsheet?